Have you ever really stopped to think about what holds the world together? I mean, what physically stops you from just falling right through the floor? Well, it turns out that a huge part of our reality, everything from the chair you're sitting on to the stars you see at night, is all built on one single, incredibly strict rule. Today, we're going to dive into the Pauli exclusion principle, the universe's unseen architect. All right, let's just jump right in with a question that sounds simple but has a completely mind-bending answer. Why can't you walk through a wall? I know what you're thinking. Atoms are mostly empty space, so what's really stopping you? And it's not just about electric charges repelling each other, which is what a lot of us learned. No, the real reason is something much, much deeper. You know, physicists have been wrestling with this idea for over a century. A guy named Paul Ehrenfest pointed this out way back in 1931. He basically realized there had to be some kind of hidden rule that gives atoms their size and stops everything from just collapsing into an infinitely dense mess. And the key to this whole mystery is found in quantum mechanics. Specifically, it's about how the universe splits all its fundamental particles into two very different tribes. And each tribe has its own, let's call them social rules. And this is really the core of it all. On one side, you've got bosons. Think of them as the social butterflies of the particle world. Like photons, the particles of light, they love to hang out together, all crowded into the very same state. That's actually how lasers work. But on the other side, you have the fermions. These are the antisocial particles, the building blocks of all matter: electrons, protons, neutrons. They have this property called spin, and because of it, they just absolutely refuse to share the same space. And here's the kicker. Since the world we can actually touch, you, me, that wall, is all built from these standoffish fermions, we all have to play by their rules. And their behavior is dictated by one very, very powerful mandate. And this is it, the Pauli exclusion principle, figured out by the genius physicist Wolfgang Pauli in 1925. It sounds kind of simple. No two identical fermions can ever be in the exact same quantum state at the same time, period. So the big question then is, what in the world is a quantum state? Well, the best way to wrap your head around it is to think of it like a unique home address. Every single electron living inside an atom needs its own distinct address. And the Pauli exclusion principle, it's like the cosmic mail carrier, making absolutely sure there are no duplicate addresses, ever. So this address has 4 parts, which are called quantum numbers. The first 3 basically define the electron's neighborhood, its energy level, the shape of its orbital, where it is. Think of it like the state, city, and street. Now, 2 electrons can actually share this part of the address, but that 4th part, their spin, that has to be different. One has to be spin up and the other spin down. It's like having different house numbers on the same street. That's the only way they can coexist. And that's it. That's the whole rule. No duplicate addresses allowed. It sounds like a tiny piece of cosmic paperwork, right? But the ripple effects from this one little rule are what build the entire world as we know it. So how does this one rule create all of chemistry? Well, since all the electrons can't just pile into that super comfy, low-energy state closest to the nucleus, they're forced to stack up in layers, or shells, each one further out. For example, a helium atom has 2 electrons, and they perfectly fill up that first shell. But if you add one more to make lithium, that 3rd electron is excluded. It has to go to the next level up. This forced stacking is literally the reason we have the periodic table and all the different elements with their unique properties. And this brings us right back to where we started. The reason you can't walk through a wall is this exact stacking effect, just on a massive scale. The electrons in your hand and the electrons in the wall are all fermions, and they are all fiercely refusing to be in the same place at the same time. This refusal creates an incredibly powerful repulsive pressure, and that is what gives matter its solidity, its very substance. But okay, the power of this rule doesn't just stop at making walls solid. Oh no, it scales up to a level that is almost impossible to imagine. It actually decides the fate of dying stars. So when a star like our sun runs out of fuel, it starts to collapse under its own crushing gravity. But it doesn't just collapse forever into a black hole. Its collapse is stopped by something called electron degeneracy pressure. That is the Pauli principle in action on a cosmic scale. The electrons are squeezed so tightly together that they push back, refusing to be crammed into the same quantum states. And for even bigger stars, gravity is so intense that it smashes electrons and protons together to make neutrons. The star collapses even further until it's saved again by neutron degeneracy pressure. The exact same role, but now it's the neutrons doing the pushing. And just how powerful is this pushback from the neutrons? A neutron star is the stiffest thing we know of in the entire universe. Its resistance to being squeezed is 20 orders of magnitude greater than a diamond's. That is a 1 followed by 20 zeros. That is an insane number. And that incredible stiffness comes entirely from neutrons, just following this one simple rule. It's truly mind-blowing when you piece it all together. The simple fact that your chair is solid, the amazing diversity of every chemical element, and the fact that dead stars can even exist instead of just becoming black holes, all of it, every last bit, traces back to this one simple, antisocial rule that governs all fermions. You know, in his Nobel Prize lecture, Pauli himself called it the correct and general wave mechanical formulation of the exclusion principle. Even he knew he had stumbled upon something truly fundamental, a cornerstone of how reality itself is built, from the tiniest atom all the way up to the largest stars. And that leaves us with one last, really fascinating thought. The Pauli exclusion principle isn't a force, not like gravity. It's more like a rule about information, about which quantum states are allowed and which ones are forbidden. So if a simple organizing principle like this can have such massive consequences for the entire structure of the universe, it really makes you wonder, what other hidden rules, what other fundamental principles are still out there, quietly shaping our reality, just waiting for us to discover them?